So, you're going on a journey to a black hole. Well, you'll need a lot of provisions, because the nearest black hole is 1,011 light-years away. This black pearl was found in the solar system called HR 6819. It was hidden in orbit with two other stars, which you can see with the human eye. Scientists have been studying this system since the 80s, but this winter it revealed its main secret. This particular black hole is considered relatively small, but despite this, its mass is 4 times bigger than our Sun, and it's 2,500 light-years closer to Earth than the next nearest black hole. But don't worry. For people, the distance of 1,000 light-years is unreachable. For example, if we were to make a model where the Earth's distance to the Sun was only 0.05 inches, you would have to travel about 4 miles to get to this black hole. But our galaxy, the Milky Way, is about 100,000 light-years wide. So the distance of 1,011 light-years doesn't seem that long in comparison. But before you jump inside this black giant, let me try to discourage you. A black hole is a place in space-time where nothing can leave its orbit. No particles, electromagnetic radiation, or even photons of light can escape from a black hole. So you should understand that a journey to such a dangerous object as a black hole is a one-way ticket. And the way black holes are born is incredible. When a star runs out of fuel, the star collapses under its own weight and becomes a black hole, like the supermassive black hole in the Messier 87 galaxy. Its mass is 7 billion times bigger than the Sun, and it was discovered by the Event Horizon Telescope in April 2019. Okay, good. I see you've already bought a ticket for a faster-than-light spaceship. Since there's no refunds, and you don't want to lose the money, it's time to get ready for the trip. Oh, feel free to leave your luggage at home. 3, 2, 1, off you go. You're leaving Earth's orbit, saying goodbye to the moon, and don't forget to cheer up Pluto by saying it is big enough to be a planet. Then you pass the highway of dark space, and here's your stop, the black hole. Put on your suit, because you're going into outer space. The first thing you see is the event horizon. The gravitational field of a black hole bends the light around its edges, so the event horizon is like a croissant for the observer. Once you reach the event horizon, though, you won't be able to get back out. You may also notice that there's some kind of chaos in this ring. Some lights move in different directions. This happens because you get a mirror effect. But we still don't know what's inside the black hole. So you decide to send in a drone first. The gravity field of the black hole quickly draws in your metal buddy. As soon as he enters the event horizon, his body begins to change its shape. It becomes elongated like a strand of spaghetti. And the closer it gets to the center of the black hole, the longer it becomes. You also notice the drone has slowed its movement and now gradually approaches the black hole center. This is another effect of this space monster. The black hole's vast mass curves not only space but also time. If you hang one watch next to a black hole and another on the wall in your bedroom, you will see that in the first watch, the second hand has barely moved, while a whole day has passed on Earth. And the more massive the black hole, the stronger the effect of slowing time. Theoretically, if you have a spaceship that can overcome the gravity of a black hole, you can fly to it and wait for a few seconds. During this time, your friends on Earth would live a whole life. The flashlight on the head of your drone has turned red. This color change has happened for the same reason. The clocks that are deeper in a gravitational well tick slower when observed from outside. This also affects the photon's wavelength. We see red light because it has the longest wavelength of any color in the visible spectrum. All these things actually happen to the drone in a split second, but it seems slow to you because of the time warp. Alright, it's time to enter the black hole yourself. The final preparation is your suit that will protect you from Hawking radiation. This radiation is created by black holes due to quantum effects near the event horizon. Hawking radiation reduces the weight of the black hole, so if the black hole doesn't absorb more mass from nearby objects, it becomes smaller and then simply disappears. Oh yes, the black holes are also mortal. But Hawking radiation can turn you into ash, and you'd lose the chance to see the black hole from the inside. Okay, now let's do what you traveled 1,011 light-years to do. One big jump, and you're caught in the gravity field of the black hole. This is the point of no return. But your distance allows you to set a stable orbit so that you can spin around the black hole like the moon around the Earth. A little higher, and you'll be thrown into infinity. A little lower, and you will be dragged into the black hole. So, theoretically, planets could exist at this distance, and even inhabited if there were the necessary conditions. A couple of minutes later, and you are approaching the event horizon. Oh, look down. Your body is so long. You are now spaghetti yourself. Look around you. The stars are turning blue. This is called gravitational blue shift. As you fall into a black hole, its gravitational field pulls the photons of light down, giving them energy. Their wavelengths are getting shorter, so the red photons change into blue and everything starts to look blue. Now you are right outside the event horizon, and the only thing you can see is a round blue beam of light above you. But soon you will stop seeing even that. So you've survived the strong gravitational field of a black hole, and the Hawking radiation didn't burn you to ash. You are now in the heart of the most mysterious object in the universe. You have front row seats, but the view is not that impressive. This is the darkest place you've ever been to. Even the usual laws of physics just stop working here. Theoretically, time goes by so slowly here that your home planet could no longer exist, and a new black hole could appear in place of our sun. But you will live exactly as long as there's enough oxygen in your suit. But what if this cosmic object is actually a wormhole that leads to another place in the universe? This is a popular theory, but scientists still can't confirm it. But if it is true, then after a while, you'll see a blue light again. Now you'll experience the same fall, only in reverse. Once you leave the singularity, which means the black hole's heart, you will be in the event horizon. The light from the stars gradually changes from blue to red. You can feel the shaking and warmth from the Hawking radiation. But then you're thrown into outer space, perhaps in some faraway galaxy. No one knows what will happen next. Are you in contact with an unknown life form? Or will the conditions there be intolerable for a human being? Or maybe you will not go to another place in space, but to a parallel universe. This theory also exists. According to it, black holes are portals to other dimensions. Simply put, there are endless copies of our universe. Every time you were faced with a choice, your twin from another universe chose something else. But let's leave that to fantastic movies. Right now, the journey into a black hole is merely impossible for humanity. We can't even reach the nearest one. But one day, we will learn more about these space objects' nature, and maybe this knowledge will push humanity forward and make us a multi-galactic civilization. We're traveling 1,000 light-years from our planet to an unfamiliar system. Here, there are two bright stars orbiting close to each other. But there is one small but very massive thing here as well – a black hole. These objects are mysterious and dangerous. They're capable of swallowing our entire world in 1 second without even noticing it. Even more, they can tear apart a huge star like our Sun. And it's these giants that usually lie at the centers of galaxies. They're so heavy that their gravity holds countless stars, planets, and stardust around them. They can weigh millions or even billions of times more than the Sun. And now, you're back on the ground, at a rocket launch pad on Earth. All you can think about is holding your breath and jumping into the heart of that black pearl. But you don't have to hold your breath because you'll be in a spacesuit, and the oxygen is included free of charge. Besides, you're not likely to ever make it to the black hole. A trip that far with the technology we have now would take tens of thousands of years. Back to your garage where you stashed your hyper rocket, which will take you to the black hole in seconds. And you're next to two stars in a black hole. First thing you notice is that the black holes aren't black. Its gravitational force pulls in not only objects, but even light itself. This makes the hole invisible. You can only see a bright ring around it. That's called the event horizon. It consists of twisted light, hot dust, plasma, and pieces of asteroids that are also trapped there. So the event horizon is the first obstacle to overcome. Okay, you put on your jetpack, open your rocket's door, and jump towards the black hole. The force of gravity begins to pull you quickly toward it. The spacesuit protects you from the enormous temperatures and levels of radiation on the event horizon. Conventional protective gear would hardly help you, so you thank your dad for stashing this super powerful protective suit in your garage as well. You begin to feel like your body's stretching unpleasantly. The problem is that gravity increases with every inch closer to the center of the black hole, and it's much stronger at your head than at your feet. Your body starts to stretch like spaghetti. That's why it's called spaghettification. No suit can protect you from that, and there isn't a single spaceship that can withstand that kind of strain. Well, this was a short video. Okay, let's rewind to the moment before the jump. You realize that to get to the heart of the black hole and survive, you don't need improved equipment, but another black hole. And it's the size and weight of it that matters here. Theoretically, you can survive falling into a supermassive black hole. It's all about the width of the black hole's event horizon. When a hole is small, about the weight of our sun, the event horizon is small too. And then its edge is remarkably close to the center of the abnormal gravitational force, which would make you spaghettified quickly and brutally. But if the event horizon is wide, it's farther from the center of the gravitational force. Then the difference of gravity pressing on your head and feet will be non-existent. So if you have enough air in your spacesuit, you can survive such a journey. So you must pick a supermassive black hole. Let's see. One at the center of the Milky Way? No, there's too much hot plasma and debris around it. You need a completely isolated black hole for a jump like this. Somewhere in dark space where it hasn't had time to gather the debris of neighboring worlds around it. You quickly open your space map and find such a black hole. One faster than light trip, and you've arrived. There it is! A huge dark nothing. There's only distorted light from distant stars and galaxies on its event horizon. To test your theory, you throw a mannequin into it. It approaches the black hole and then slows to a standstill. But it's just an illusion. The black hole is so heavy it can warp both space and time. So to the observer, the dummy is frozen in the event horizon, but it has long since entered its heart. The dummy didn't get spaghettified like you did when you fell into a small black hole, so now you're confidently jumping after it. Remember that even if you feel fine, it's still a one-way trip. Once in the black hole's field of attraction, nothing can escape its embrace, no matter how powerful a rocket you have or how hard you flap your arm. You're now at the edge of the accretion disk. Every second here equals weeks or months on Earth. You're traveling through time. Our home planet may already have flying cars and skyscrapers several miles tall all over the place. But for you, it's only a couple of minutes. Whoa! All the light you see from the stars has turned red. That too is because of gravity. The light we see is waves, but the black hole stretches them out. The short wavelengths of blue become long and red. Great! You've passed the event horizon and are now heading into black nothingness. You look up and see a thin ray of light. The last thing you see, in fact. After that, there's just black void. No one knows what happens next. Some theories say black holes can be portals to another dimension, or to another place in the universe. By jumping into a black hole in our galaxy, you can jump hundreds of thousands of light years away from our home. In that case, you will experience your fall in reverse. First, you see a small but expanding beam of light. Then, red starlight returns to blue. And before you know it, you're back on the event horizon. And soon after, you're free of the black hole's pool. But scientists still can't confirm this theory. Okay, that's too grim. So just this time, we'll bring you back to Earth in the company of your friends. They praise you for your accomplishment of surviving the center of a black hole. Now you're the heart of the company, and no black hole can scare you. But even the biggest black hole in space isn't as scary as you might think. They have a lifespan. That radiation I mentioned takes energy from the black hole. If it doesn't have food around it, the hole starts to deflate like a balloon, and eventually there's nothing left. Another fear around black holes is that we can create one at home. Indeed, inside the Large Hadron Collider, scientists conduct experiments with small particles colliding at high speed. There are huge bursts of energy, and some scientists believe this energy is enough to create a microscopic black hole. It will begin to absorb its surroundings and grow. First, some small objects in the room where it was created. Then, the entire lab. The hole continues to grow and is already consuming our whole planet. It changes the balance of power in our solar system and absorbs the planets one by one. When those are finished, it's time for dessert, the sun. The light upper layers of plasma are stretched into long spaghetti and pulled toward the black hole. Then, layer by layer, our star collapses into the dark abyss. When the sun is half absorbed, the black hole shoots a beam of energy and light outwards and continues to consume the sun. In mere moments, there's nothing left of our solar system. That's how some people describe the end of the world. But even if we do manage to create a microscopic black hole, we'll be safe. It'll be too small to absorb big objects, and it will only feed on small atomic particles. Black holes emit energy as well as consume it, so our little one won't have time to grow. It'll lose more than it finds in a fraction of a second. So what you'll see is a momentary flash and then nothing. Although creating a stable and controlled black hole may even be useful, they emit enormous amounts of energy that we can use. A black hole the mass of Mount Everest could power all of humanity. Of course, black holes are still dangerous, but we can watch them and study our universe. If we stay far enough away, of course. So, you decide to put a padlock on that garage door. For now. So, you're standing on a diving board in the middle of an open space. You look down, but that's not a pool. It's a giant black hole. Well, what the heck. You start swinging and then you jump. The gravity of the black hole grabs you, and you pick up speed. Just a little more, and you'll enter the dark abyss. But you're not afraid. You're sure you can survive the fall into the black hole. Besides, you have a clear goal to travel through time. But first, let's figure out how it works and why time stops near a black hole. This is the space-time grid. It's what our entire universe is made of. And just like a regular grid, it sags if you put something heavy on it, like me. For example, let's put the planet Earth here. You see a little funnel that is formed around the Earth, and if you put a small ball next to the planet, it'll roll into the funnel. That's how gravity works. The heavier the object, the more it bends space-time. By comparison, here's the Sun. It's almost 333,000 times heavier than the Earth, so it makes a really big funnel. So big that all the planets in our solar system move around that star inside that funnel. So now, let's put a black hole on a space-time grid. Its centers are infinitely heavy, so they create a limitless deep well. And anything caught in the black hole's gravitational field can never leave it, not even moving at the speed of light. Okay, their gravity is infinitely strong, but why do they slow down time? It's all about the speed of light. According to physics law, the speed of light must be the same at every point in our universe, even in a black hole. So, for our experiment, we take this ball, a photon of light that can travel 671 million miles per hour. You could get from Earth to the Sun at that speed in 8 minutes. That's how long it takes light to travel from our star to our eyes. So, when you're looking at the Sun, you're looking back in time 8 minutes ago. By the way, don't look at it directly. Now, the critical thing to remember here is that velocity consists of two physical quantities: space, miles, and time, hours. We'll use that later. Now, let's look at the black hole in our space-time grid. In three-dimensional space, it appears like this. But if we assume that space is two-dimensional, our grid looks like this when viewed from above, just a lot of squares. And this is the black hole right in the middle. If you look at the grid from the side, you'll see a straight line. And the black hole here looks like a pit, or like an endless well. Now, let's follow our photon of light in three-dimensional space. Here, it's moving toward the black hole, and then it falls into the well of the black hole, and it continues its motion at a constant speed. Now, the side view. Again, the photon moves from left to right and then falls. Its velocity doesn't change. The problems begin if you look at the experiment from above. When the photon of light moves in the distance of the black hole, its speed is stable. But then it goes down into the well. First, it slows down and then it just stands still. But it's moving downwards. The photon moves in an arc down the well in the lower dimension without changing its speed. But in the higher dimension, it traveled a minimal distance at the same speed. Usually, this would mean that the photon was moving at a low speed in the second case, but not in the case of the speed of light. Remember, it must be the same at every point in the universe. The number 671 million miles per hour shouldn't change. So, we change the very parameters of that number, time. Time itself must slow down so much that this slight movement of the photon, when you look at it from above, was at the same speed, 671 million miles per hour. But if you go down and look at this well much lower, you see that its walls are almost vertical. So, a photon of light would be moving in a vertical trajectory. That means that if you look at it from above, the photon will just be standing still. Again, its velocity can't change, so time will vary. At that point, it should just stop. This is what happens near a black hole. Now, if you look at a black hole, you can see this effect in action. It swallows up the light around it. But as for an observer, it seems to you that the light stays in orbit around the black disk. In fact, at that moment, the photons are still moving at the speed of light inside the black hole. It's because time has slowed down there so much that you feel like the light has stopped there. This disk is called the event horizon, the point of no return, the last stop before you go into the black abyss. And at the very center of the black hole is the singularity. This point of space is so dense that if you tried to describe it with any numbers or physical quantities, they would all tend toward infinity. Simply put, all the laws of physics we know just stop working here. So scientists can't say exactly what awaits you in the singularity. Before you make that jump into the black hole, let's drop a space probe there with a blue light that flashes once per second, and let's attach giant clocks to it. You see the probe falling into the black hole, gaining speed, but then it starts to slow down. Moreover, the probe flattens out and seems to spread out around the black hole. And then you notice that the blue beacon on the probe has changed its light. It now flashes as red. It's because the light is a wave. Blue is a truly short wave with a high frequency, but the black hole's gravity acts on this wave, stretching it out. The light waves get lengthened and become broader and less frequent. The new wavelength and frequency match with the red color. It's called redshift. Also, the probe blinks now not once a second in short beeps, but lights up and goes out for a long time. It's because of the time warp. If you, as an observer, look at the clock on the probe, the second hand there barely moves. However, the clock on your hand works as usual. But if you could be in a black hole, time would seem normal to you, and the arrow on the clock would move as it did before. But the hands on the clock outside the black hole would move like crazy to you. That's because time goes much faster outside the black hole. Oops! Your probe just got ripped apart. That's because of the substantial difference in gravity that acts on the probe. The black hole's gravitational force increases with every foot of approach. That is, if you were to extend your hand toward the black hole hard, the gravity on your fingers would be much stronger than on your shoulder. This force would cause your fingers to lengthen, simply like spaghetti. That's why many people think it's impossible to survive falling into a black hole. But scientists think you could survive without a problem. Hey, maybe they should jump first just to make sure. The thing is, you have to pick a black hole as big as possible, like the ones at the centers of galaxies, for example. That bright spot at the center of the Milky Way also has a black hole. It's about 1 million times heavier than the Sun. And this is the Messier 87 galaxy, one of the most massive galaxies among our neighbors. In 2019, humanity got its first ever photo of the black hole at the center of this galaxy. It's about 6.5 billion times heavier than our Sun. So, it's the perfect place to make your jump into a black hole finally. Let's go. At first, you feel a strong acceleration as the incredible force of gravity grabs you. But in the case of a supermassive black hole like this, the gravity doesn't change as dramatically. That's because of its size. Right now, the gravitational force on your legs is about equal to the gravitational force on your head, so you don't turn into spaghetti, and you feel comfortable. You see that the light from the stars and all the space around you has begun to shrink at a certain point. It means that you have already passed the event horizon and are now moving toward the black hole's heart. As a result, the light of the universe becomes a small dot for you and then disappears altogether. If we look at our space-time grid, you're already falling into a well. Time is completely stopped for you. However, the rest of the world continues to move steadily through time. If you could now look at the Earth from a black hole, you would see a time-lapse, an accelerated video of how the months and years go by on our planet. If you had a jetpack that had an incredible engine to pull you out of the black hole, then you can make a jump forward in time. In 1 second, centuries on Earth could pass in the heart of a supermassive black hole. But this only works one way. You can't go back in time. But for now, you keep falling into the black hole. Beyond that, no one knows what'll happen to you. We only have theories about wormholes and white holes that might transfer you somewhere else in the universe. So, enjoy your trip, and just think about all the frequent flyer miles you're racking up.